Welcome to the video for 2.1 Chemical Equilibrium. You need to look at your textbook to help with this, then look at pages 20 to 21. Lesson objectives for today are to know that Kc is the equilibrium constant calculated from equilibrium concentrations for a system at constant temperature. So before we start, we need to stop. So before we get on with this video, if you haven't already, you need to revise everything that you've done about reversible reactions in Year 12 before you continue. If you don't, then none of this video will make sense. So make sure you do this before you continue. So chemical equilibria. There's a very lengthy quote here which I'm just going to read to you. If the concentrations of all the substances present at equilibrium are raised to the power of the number of moles they appear in the equation, the product of the concentrations of the products divided by the product of the concentrations of the reactants is a constant, provided the temperature remains constant. Now that sounds really horrible, but I'm going to show you on the next slide a better representation of this, and hopefully it will make sense. So here is in a more mathematical form, which is less wordy and should hopefully make more sense. So for an equilibrium reaction, there's this obviously made up reaction here. A plus BB goes to CC plus DD. Now in this chemical equation, the capital letters represent chemicals and the small letters represent a number. So you might have 2A plus 3B goes to 1C plus 4D, for example. So the little letters are numbers and the capital letters are representing chemicals. So if this was true, if this was our chemical reaction and it's a reversible reaction, then at constant temperature, Kc, which is the equilibrium constant, would be equal to the concentration of C raised to the power of the small letter c times by concentration of D raised to the power of the small letter d divided by the concentration of A, capital A, raised to the power of small a times by the concentration of B raised to the power of the small b. So what this means is that you've got the concentrations of the reactants and products raised to the power of the number that represents how many moles are reacting in the equation. And those square brackets just are representing the equilibrium concentration in moles per decimeter cubed. So this is our expression for the equilibrium constant. So what happens to the theoretical yield of a reaction if Kc increases or if Kc decreases? So if Kc is a big number, then if Kc is a big number, it's representing the products divided by the reactants. So if Kc is a big number, that means you've got more products than you've got reactants. So that means the equilibrium is over to the right. If you've got a small value of Kc, then that means that you've got more reactants and products. The equilibrium has shifted to the left. So now we're going to look at the value of Kc. And the Kc is a constant, but it is affected by a change in temperature. So when you're given the value of Kc, it only applies for a certain temperature. However, it's not affected by a change in concentration of reactants or products, it's not affected by a change of pressure, and it's not affected by adding a catalyst. And we'll talk about that, about the value of Kc in lesson 2.3, where we'll talk about how temperature affects the value of Kc. So we don't need to worry about it now. Now the units of Kc vary depending on the expression, and this is a common cause of difficulty in exam questions, but you can work them out using the Kc expression. So I'll talk you through two examples here. In the first example, you've got nitrogen reacting with hydrogen to give ammonia, which of course is our Haber process that we know and love from GCSE chemistry. And the Kc expression for that is the concentration of ammonia raised to the power of 2, because there's 2 ammonias in the equation, divided by the concentration of the nitrogen times by the concentration of hydrogen, and the hydrogen is raised to the power of 3 because we've got 3H2 in the balanced equation. So that's our value for Kc. So if we want to know what the units of Kc are, then what we need to do is plug in the units for the concentrations. Now the concentration is moles per decimeter cubed, so that's moles dm to the minus 3, and if we put those into the expression that we've written, so we've got the expression for Kc, if we put the units in and then multiply them out and cancel them, we can see that the units then become 1 divided by moles per decimeter cubed, which is squared. And those of you that are confident with your maths will realise that that means that the unit is then moles to the minus 2 decimeters plus 6. Alright, our second example is a lot more simpler, because for that reaction H2 plus Cl2 gives 2HCl. The Kc expression is HCl raised to the power of 2, because you've got 2 HCl's in the equation, divided by the H2 concentration times chlorine concentration. So in that case, you've got 2 concentrations on the top and you've got 2 on the bottom. So even without plugging your units of concentration in there, you should be able to see straight away that that's going to cancel out. But if you do put them in, you've got moles per decimeter cubed on the top times by itself, and then you've got the same thing on the bottom. So that cancels out and you have no unit. So what we need is a stepwise method for calculations involving Kc. The first thing you need to do is write the balanced equation including state symbols, which is really important, otherwise the rest of it won't work. Step 2, you then need to calculate the number of moles of each chemical equilibrium. Step 3, divide the number of moles by the volume in decimeters cubed to get the equilibrium concentrations in moles per decimeter cubed. Quite often in questions you're not given what the volume is, in which case just represent the volume with V, and if you're not given the volume it's probably going to cancel out. Step 4, from the equation that you've already constructed, write out the expression for Kc, and then finally step 5, substitute values from the third step and calculate the value of Kc with any unit. So here's an example calculation where we talk about 1 mole of methanoic acid reacts with 1 mole of ethanol at 298 K. When equilibrium is reached, it's found by titration that 2/3 of the acid has reacted. Calculate the value of Kc. So there's the step 1 is to write out the balanced chemical equation, which is written there. So you've got methanoic acid plus ethanol giving the ester and water. So it's quite a simple example because you've got 1 mole of methanoic acid reacting with 1 mole of ethanol to give 1 mole of ester and 1 mole of water. So if you look at the number of moles initially, it says you've got 1 mole of methanoic acid and 1 mole of ethanol. So you've got 1 mole of each of those, and you don't start with any product, so there's 0 moles of each of those. So at equilibrium, it says 2/3 of the acid has reacted. So if 2/3 of the acid has reacted, that means we've got 1/3 left. So that second line just shows 1 minus 2/3 gives the equilibrium concentration of 1/3 divided by V. Now if you look at the balanced equation, 1 mole of methanoic acid reacts with 1 mole of ethanol. So if we have used up 2/3 of methanoic acid, then we've also used up 2/3 of a mole of ethanol. So we can write out our equilibrium concentration of ethanol is going to be also 1/3 divided by V. If we look at our products then, we should realise that 1 mole of methanoic acid gives 1 mole of ester and 1 mole of water. So initially we started with 0. If we've used up 2/3 of a mole of methanoic acid, then that means we must have 2/3 of a mole of the ester and 2/3 of a mole of the water left. Which means our equilibrium constant then of our products, for both of them, it's 2/3 divided by V, where V is our volume of the equilibrium mixture. So if we put these figures into our Kc expression, then it becomes 2/3 divided by V times 2/3 divided by V divided by 1/3 divided by V times 1/3 divided by V. And if you cancel all the V's out and you multiply that out, you come up with the figure 4. So here are our lesson objectives, which were to know that Kc is the equilibrium constant calculated from equilibrium concentrations for a system at constant temperature. If you haven't understood everything in the video, then either rewatch it or have a look in your textbook and make sense of it before you turn up to the lesson.